All right, on to yet another special type of limit problem. They're all special, aren't they? These are the ones where x is approaching infinity. That's not quite the same thing as if your limit equals infinity. Like if we had an asymptote and we were approaching the asymptote from the left, it might shoot up like that. Approaching from the right, it might go down to negative infinity. So those where the limit equals infinity, I'm just talking about where you plug in infinity for your limit. Now obviously this is a special case, and we'll get to the details right away. All right, so what's going on with these? Well, first of all, basics first. If you plug in infinity for x, you're going to get infinity, right? That's pretty obvious. Makes a lot of sense. If we had plugged, x squared in, like the limit as x approaches infinity of x squared, also infinity. Infinity squared, infinity, both giant numbers. We're just going to put infinity. What happens though if you're dividing by x? So the way you want to think of this is that the bigger the denominator gets, the smaller a fraction gets, right? 1/5 is a lot bigger than 1/100th, because a hundredth has a bigger downstairs, therefore it's a smaller overall fraction. So you can bet your bottom dollar, if you put 1 over a jillion or infinity or whatever, you're going to get 0, or so close to 0, it might as well be 0, and that's what limits are all about. So 1 over x, as x approaches infinity, the limit is 0. 1 over x squared, the limit is 0. 1 over x cubed, the limit is 0. The pattern is anytime there's an x downstairs of a fraction and x is going towards infinity, that fraction is going towards 0. So obviously those are a little bit simplistic. This is the kind of thing you're more likely to see, either separately or as part of a bigger problem. So the key thing is you got to ignore constants. If there's an x involved, like right this thing, infinity squared is infinity. So we've got infinity squared minus 2. So we just need to think about it and say to ourselves, is this probably going to be infinity, or does that 2 do anything? 2 doesn't do anything, right? Because by the time you're up to infinity, infinity plus or minus 2 or whatever, 2 is nothing compared to infinity. So you can pretty much ignore it. Infinity here, the x squared term is the dominant term, and therefore the limit is infinity, not infinity minus 2. The limit of a constant, however, if we don't have any x squareds or x's or anything to worry about, the limit is just going to be the constant, because there's no x to plug into, right? If it's just 3, it doesn't matter x is going to infinity. Z could be going to infinity too. Y could be going to infinity. None of it matters because there's nothing to plug infinity into. It's just 3. So we're just going to take that 3 and take it right to the other side. The limit is 3. Even if x had been approaching 2 or 3 or 5 or negative 10, the limit of a constant is just the constant. So now this last one is sort of a grab bag of a bunch of different things. The limit of anything with x downstairs is 0, right? So the limit of this term is just 0. The limit of this term is just 0, so you got 0 minus 0, no big deal. Oops. And then we've got a plus 3. So in this case, in this previous one, the negative 2 didn't matter because it was infinity plus 2. Big deal, 2's nothing. But if you just got a 0 and 0 plus 3, wow, 3 is now the big boy on the block, and this limit is 3. So it just depends on what comes around it. If there's powers of x, like x squared and x cubed, like there were here, that's going to be the dominant term, and you can ignore everything else. But if you got a bunch of zeros, then the constant can actually end up being the biggest number and what the limit is equal to. All right, just want to point out, just like we factored upstairs and downstairs previously, if we had a 0 over 0 indeterminate situation, like this first problem, what you'd do is you'd factor out the x minus 2 from the top and bottom and then cancel them, right? Same thing here. If we plug in infinity right now, we're going to have infinity upstairs, infinity downstairs. It's going to turn out that maybe they're not the same infinity because one's infinity squared, one's infinity, but who knows what will happen. So what we're going to do is we're going to factor the bottom. X minus 2 will stay upstairs, but then you probably saw the x squared minus 4 and said to yourself, wow, we should factor that, right, before you even thought about it. All right, so then x minus 2's cancel, and we just get the limit as x approaches infinity of 1 over x plus 2. Now we got a situation where the answer is pretty obviously 0, because as x approaches infinity, you can ignore everything except the big term, right? The big dog in this denominator is the x, because it's going towards infinity. 2 is just 2, so we'll sort of ignore that. And the limit of 1 over x, or 1 over infinity, is 0. Similar thing will happen down here. This is actually a factorable difference of cubes. If you don't remember how to do that, by all means go back and check out the factoring videos in Algebra 2. But the main moral of the story is this is going to factor to x minus 2 times x squared plus 2x plus 4, which is not coincidentally what I have downstairs here. So that cancels there. And now what's the limit of x minus 2 as x approaches infinity? Well, it's the same thing we had in the previous slide. Infinity minus 2 is still pretty much just infinity, right? That 2 really doesn't make a big dent in something as huge as infinity. So there you go. And now if you look back at this problem, now you know the answer is infinity, you can kind of see that makes sense. Infinity cubed is bigger than infinity squared. By how big a factor? Infinity, right? If you plug in, you know, if you plug in 10 for x, you would get 1,000 over 100. If you plug in 1,000 for x, you get a million over a billion, or a billion over a million, sorry. The top number is always quite a bit bigger than the bottom number. So it makes sense we got infinity. All right, so it's going to turn out the big shortcut on these is to ignore everything except the highest power term upstairs and downstairs. So what we're going to do is, since x is approaching infinity, I know that 2 is not going to end up being a hill of beans compared to x squared, because I'm going to be plugging in infinity for x. But then again, x squared is kind of a hill of beans compared to x cubed, because when you plug in infinity, x cubed is going to be infinity times bigger than x squared. It's got a whole other infinity multiplied in, right? So that's why this is the big dog on the numerator, and everything else is just chopped liver. So we're just going to scribble all that out. And then downstairs, we got a 3x cubed term, which is obviously infinity cubed. That's a ridiculously huge number. And this negative 4 is like nothing compared to infinity. So we're going to scribble that out. Now, we just got a pretty basic fraction we can cancel stuff. This is reduced to x cubed over 3x cubed. X cubed cancels, and we just get 1/3. And it turns out that is the answer, because the limit of a constant, there's no x's to plug infinity into anymore, right? So there's 1/3, and it's not a coincidence. That is, you know, this top x cubed had a coefficient of 1, and the bottom had a 3, and that's where that 1/3 came from in our answer. It's kind of the shortcut we'll look at in the horizontal asymptote video coming up, using limits to find horizontal asymptotes. It's basically just if you have matching powers like x cubed upstairs and downstairs, or x squared upstairs and downstairs, or x to the 4th upstairs and downstairs, if those powers match, if you have the same power of x on both top and bottom, the limit when you plug in x equals infinity is just going to be the ratio of the coefficients. You know, that'll cancel that, and we'll just be left with that 1/3. All right, we'll do the same thing in this next problem. We're going to ignore everything except the highest power in each of the denominator and the numerator. So upstairs, x cubed versus 8. X cubed is the big number. And then of the 3 terms downstairs, x squared, 2x, and 4, x squared is the highest power. Just going to ignore that, which just leaves us x cubed over x squared. Now this time the powers don't match. In the previous problem we had cubed over cubed. This is cubed over squared. So when you reduce this, you can just pull out an x squared from top and bottom. So this will become x squared. That'll become a 1. Oops, sorry, this will become an x. So it just reduces to x. So what's the limit as x approaches infinity of x? It's infinity, right? So you can see how it's really nice just to be able to cancel out everything except the biggest term. All right, last one we'll do on this page. Even though x isn't that great, isn't that big, compared to 2, it's the big dog. So we're going to scribble this out and just keep our x. The biggest term downstairs is 3x cubed. We're just going to ignore the 4. So and then if we cancel this out, we can pull an x out of top and bottom. So that x will become a 1, and the x cubed will become an x squared. So we get 1 over 3x squared. And what is the limit as this approaches, as x approaches infinity? Well, we've got an enormous growing without bound type denominator. There's a 3 in front of it, but that just makes the situation worse. This is approaching 0. 1 over a bajillion is 0. So our shortcut, cross out everything except the biggest power upstairs and downstairs. All right, what's going to happen with negative infinity? It's going to turn out the exact same rule applies. We're just going to ignore everything except the biggest dog. So I get x squared. By the way, I'm approaching negative infinity here if you can't see that. So what that means is instead of plugging in positive infinity, we're plugging in negative infinity. But we'll just do the same thing, 3x cubed. We'll cancel x squared out of each, so that just leaves us with an x downstairs and a 1 upstairs. So that's 1 over 3x. and 1 over 3x, plug in negative infinity, and you get 0. So it turns out if the denominator is massive, like bajillions, whether it's infinity or negative infinity you're plugging in, either way you got 0. You could look at it a slightly different way, which is, well, hey, are we approaching 0 from the right or left? You know, is it? So it turns out we're kind of approaching 0 from the negative, because if we plug in negative infinity for x, you're going to get 1 over a negative 3 jillion, you know, whatever that giant number is downstairs is going to be negative. So there's actually kind of a negative 0 is a way of thinking about it. But most teachers don't think about it that way. Most of them are just like, oh, it's 0 and you're done. If they insist on putting a plus or minus in front, you can figure out the sign based on the sign of the infinity. All right, same thing on this bottom one. We're just going to ignore everything except the biggest power. So x cubed we keep. Negative 8 we throw away. Downstairs we keep x squared. Throw everything else away. Now the limit is so this reduces to, we can pull out an x squared from both. So if you cancel out the x squared, you're left with just an x upstairs. So x over 1 is x. And of course, what's the limit as x approaches negative infinity of x? Well, you just plug in negative infinity and you get negative infinity. All right, so that's the key. When you're plugging in negative infinity, it can just mess with the signs. It might mean that your limit is negative infinity instead of positive infinity. Not the end of the world. All right, hard ones. What's hard about these? Well, for one thing, it's not factored, and I don't know what the biggest power is, right? That shortcut I showed you, where if you have a big polynomial, just cross out everything except the first term. Not easy to do when there is no first term to cross out. What you'll need to do is look at this and say, well, gosh, I could FOIL this out. And it would take me a little while, and some teachers are really mean. They'll give you like a 3-way FOIL or whatever. But really, all you care about is the biggest term, right? The biggest power of x. So the way you're going to get that biggest term when you FOIL stuff out is you'll take the 2, then you'll multiply it by the power of x in the term that has x in it in the second set of parentheses right here. And that would be that x. And then you'll take the x term from the last set of parentheses, which is negative x. And then downstairs you do the same thing. So the highest power of x I'm going to get downstairs would be if I took this 3x and that x and multiplied them together. Now if you don't trust me on this, you can just pause the video and FOIL this out, and you should get the same first term that I get. So upstairs I get negative 2x squared, and downstairs I get 3x squared. And remember, take the limit of this as x approaches infinity. But of course, first I want to cancel these x squareds because they're a pain. So it looks like the limit is negative 2/3. Because with those x's gone, I don't even have to plug in infinity. I just get the coefficients. All right, this last couple, kind of tricky. Let's see what's happening. So recall that the deal with negative exponents is you just got to move them across the fraction line. So 5 to the x stays 5 to the x. But 3 to the minus x downstairs is going to end up coming upstairs and being a 3 to the positive x. So we're just taking the limit of this, 5 to the x, 3 to the x, as x approaches negative infinity. So that means when I plug in infinity, I'm going to get 5 to the negative infinity times 3 to the negative infinity. Now you might be thinking, and this is kind of a trick question I made up, because you might have been thinking, hey, 5 to the infinity, 3 to the infinity, those are enormous numbers. The limit of this is infinity. But it's actually, that's backwards, because its x approaches negative infinity, which means the exponent that 5 is getting is negative infinity, and 3 is getting a negative infinity, which is like 1 over 5 to the infinity times 1 over 3 to the infinity. So actually, this thing's approaching 0. Because that 5 to the infinity and 3 to the infinity are downstairs, which means, hey, crazy huge denominator with a 1 over it, which of course, fractions with giant denominators are actually 0. All right, last one. Now this one's a little confusing in that I don't know of a technical way to do this one that makes any sense. What you just have to do is either plug into your calculator or think about it. And I'm going to recommend the calculator. I don't actually know how. The only way I know how to do this easily is just by plugging in with a calculator. So if you're not sure what's going to happen, you could just try plugging in a big number. because x is going towards infinity, right? Now in your calculator, there is no infinity button. But you could try plugging in 1,000 or 1,000,000. And I think if you do that, you'll end up blowing out your calculator. Like, it just can't handle numbers that big. It turns out 5 to the x is just super huge. It grows really fast. So what I tried doing was plugging in 20. So when you plug in 20 for x, what you get is 30 million. So obviously we're well on our way to building towards positive infinity. So it just turns out that exponentials, that is a number raised to an x, grow a lot faster than a polynomial type deal like x to the fifth. So that's just something that maybe you'll be able to use either in a limit problem on the test or in the future. Just kind of interesting that even though both these things are growing really fast, 5 to the x and x to the fifth both get way bigger. As you know, as you go to the right and x gets bigger, those both get huge, but exponentials get big quite a bit faster than regular polynomials. All right, so those are the shortcuts and tricks I know. But when in doubt, plug in numbers. So if you're not sure if it's one of these weird ones like down here, just try plugging in 100, try plugging in 1,000, see if you can detect the pattern of things going berserk.